Welcome back to Analog Electronics. This is lecture 39 and today we are going to start the last module of this course, which is voltage regulators. So, what is the problem? First of all, let us try to understand what a voltage regulator is. All right. So, the problem is that my analog signal, analog circuit, let us call it okay. So, I have got some analog circuits on my chip. I also might have some digital circuits. Okay. And these all require power, these all require a power supply. So, on one side they are connected to ground, on the other supply, on the other side I need to connect them to a power source. Okay. Now, when I do such a thing, invariably, I mean in the crudest possible case, you might have these two as the same power supply. Okay. And this wire is going all the way to the battery or the power supply. Now, it is all very nice, this all looks very nice, but the problem is that the battery will have some source resistance. All right. Now, when you are clocking your digital circuit up and down, right, let us say there are flip flops, there are AND gates, NOR gates, NAND gates, right, some signaling is happening. When there is a change in the output of these gates or when there is some activity in the flip flop, then current is going to be drawn at that instant when there is change. So, at the edges of the clock typically, right, for example, if it is a D flip flop, then the output D is going to become equal to Q at the edge of the clock. So, at the edge of the clock, this digital circuit is going to draw some current, otherwise the digital circuit is going to stay silent. Okay. So, if you look at the current profile of the digital circuit, it looks like this. Right, there are impulses, current impulses, and all of those current impulses are at the edges of the clock. Now, what is going to happen? This current is going to be drawn. The voltage that you see over here, invariably, what is it going to look like? It is going to look like the original battery voltage minus those impulses times this resistance. All right. And that is going to go to my analog circuit, and then the analog circuit, the power supply itself of the analog circuit is behaving in this funny way, right. So, imagine your analog circuit, right, suppose it is some differential amplifier, actually differential amplifier is a very good example. If it is not a differential amplifier, the outcome is going to be very harsh. Okay. But suppose this is there is some differential amplifier over here, right. The power supply is bouncing like this. Okay, at the edges of the clock. What is going to happen? It is as if the power supply is a constant plus some signal. So, it is as if you have applied a signal over here, and through this common gate kind of structure, that signal is going to get amplified at the output. All right. So, this is generally very bad news. For an analog circuit, this is all very bad stuff going on. This could have come from the digital circuit, this could have come from any other source, this could have come from the analog circuit itself, right. Maybe the current in the analog circuit is going up and down like that of a power amplifier, right. The current is going up and down like that of a power amplifier, right. That is going to get amplified in terms of voltage in some other analog circuit, some differential amplifier you have got. The power supply is going up and down, and therefore, that will get amplified. Okay. So, in general, this is all very bad news. You do not want this power supply voltage to move at all. All right. Here I said this is the source resistance of the battery. It is not just the source resistance. You could also have resistance in the wire. All right. Especially if the wire is long, it is going to have resistance. What is going to be worse is if the wire has inductance, and invariably that is what happens. You know Murphy's laws, right. What does Murphy say? Murphy says that if something can go wrong, it is going to go wrong. So, what typically happens is that this wire is not just resistive, it is also very inductive. Why is it inductive? Because it is a long thin wire. Okay. Typically, when you make a circuit, when you make an integrated circuit, the integrated circuit is going to be packaged inside a package, right. You have got an IC, and then this IC is going to be packaged inside a black plastic package, and which you are going to buy, right. So, that black plastic package is slightly bigger, and there are pins on the black plastic package, and the actual pins from the IC are bonded to that plastic package through these thin bond wires, which are made up of gold. Okay. They are made of gold because gold is the most malleable element, metal, right. You remember, ductile and malleable element, that is gold. So, typically these wires that connect the actual piece of silicon to the package, they are made up of gold. They are very thin, diameters could be as low as 0.025 millimeters. Okay. That could be the diameter. 25 micrometers could be the diameter of that gold wire, right. So, if you have a thin wire, what is it going to present? It is going to present inductance. So, these wires present inductance. Then this power supply wire, which is inductive already. So, this is already an inductor that goes through a long wire, which is again not very thick, right, all the way to the power supply. That is also inductance, right. So, everywhere you have inductance, and now this spiky current, right, this current which looks like a sequence of impulses is coming through inductance, right. If I comes through inductance, what is the drop? L times di by dt. Imagine this is already impulsive, right, full of impulses. Di by dt is going to look crazy. Okay. Di by dt is going to look like this. Right, it is going to look horrible. So, effectively this power supply voltage is not even going to look like this. This is if you are lucky. Typically, it is going to look like this. Okay, which is even worse, and L di by dt is going to go up as the frequency goes up, right. The shorter these pulses are, di by dt is going to blow up even more and more, right. So, the amplitude of this is going to be pretty large even when the current is small, right. This current might be of the order of some 100 microamperes, all right, but this amplitude is going to be fairly large, because what matters is di by dt, not the current itself, all right. So, this is a problem, right, and whenever there is a potential problem, Murphy has said that that problem is going to crop up in your life. Okay. So, this is I am identifying this as a potential problem, and guess what, this inductance in the power supply wire is everywhere, all right. So, we have a problem. The problem is that the power supply to the analog circuit is not good, it is not the VDD that you want, it is not a constant voltage. So, this is where we are going to make a voltage regulator, right. This is all that I have discussed so far, is to motivate to you the requirement of a circuit called a voltage regulator. What does a voltage regulator do? So, nothing much, it is a 3 terminal circuit, one terminal is ground, the other terminal is the dirty power supply, and its output terminal is the clean power supply. And then what we are going to do is, we are going to give the analog circuit, the differential amplifier is going to draw power from this clean power supply, okay, and we have to figure out what is inside. All right, so far so good. I need to make a 3 terminal circuit such that it takes a dirty power supply and converts it into a clean power supply with respect to ground, assuming ground is fixed. This is the problem at hand. How do we do such a thing? One very straightforward trick is to use an op amp. So, imagine an op amp, and from somewhere I give you a constant voltage. Okay. This is not the source of power, but this is just a constant voltage. Somehow let us say I manage to make a constant voltage, which is not a source of power, it can't generate power. Okay. A lot of people make this using a Zener diode. Have you heard of a Zener diode? The symbol is like this. Okay. The Zener diode has a fixed breakdown voltage. Okay. So, if I push current through a Zener diode, then the voltage that it creates is a constant voltage. This is the idea. All right, a lot of people use this Zener diode. So, I take this Zener diode and create a constant voltage. I push a current through a Zener diode, I bleed a current through a reverse biased Zener diode and create a constant voltage. And now, this is from the dirty supply. The op amp needs power. Okay. From the dirty supply, I am taking power for the op amp. Now, what we are going to do is, we are going to use this and make our non-inverting amplifier. Okay. what happens? What is this output voltage? This output voltage will be 1 plus R2 by R1 times the original reference voltage. And will it be bouncing? No, it will not be bouncing as long as this does not leak out. Okay. As long as the effect of the dirty power supply does not come into the output, right. Typically, it will not, because this is a feedback circuit, right. Feedback is going to make sure that this output is related only to Vref and not to the dirty supply at all. Okay. So, portion of the dirty power supply will still leak out, right, and that is, I mean, for a practical voltage regulator, a portion of the dirty supply will still manage to leak out. That is called power supply rejection. How much of the dirty power supply is rejected in the actual power clean supply, that ratio is called power supply rejection. But otherwise this circuit looks okay. Okay. So, some non ideality is there, that some dirty power supply might still come out, otherwise this looks okay. If you want to, there are two things over here. One is loop gain, right, closed loop gain of this circuit. The other is that the amount of power that you can push. This op amp has to now be able to drive all the power demanded by the actual analog circuit. Okay. So, all of that current has to come out through the op amp. All right. Generally, that becomes a big bottleneck. What people do is, instead of doing just this is okay, right, this circuit is okay, this circuit works, but it can't drive a strong load. It can drive only as much as the op amp can provide. The op amp output current is somewhat limited, right, you have to design the op amp, right. So, that op amp, differential amplifier, all of that, the output current that is coming out of the op amp typically is not very large. Remember, this is a large output impedance, right. The op amp output has a large impedance, output impedance is quite large. So, you do not want it to drive large amounts of current. Instead, what people do is, they put a buffer in between. Let us redraw. Okay. What is this? This is a common drain circuit. Common drain circuit has a low output impedance. Okay. If you want to analyze this circuit, what is the output voltage going to be? Is it going to be related to the common drain at all? No, it is not, right. If you call this as Vref, then the op amp will make sure that the feedback voltage, the voltage at the minus terminal is also Vref. If this is Vref, the voltage at the minus terminal has also got to be equal to Vref, as long as there is negative feedback around the op amp. So, this is equal to Vref, which means that this current is Vref by R1. Where is this current coming from? It is coming through this, right, which means that the output voltage is Vref plus Vref by R1 times R2, which happens to be 1 plus R2 by R1 times Vref. Okay. So, the output voltage has nothing to do with this MOSFET over here. This is just pushing the load current, right. You are drawing load current, you want a lot of current. Who is going to give you the current now? All of that current is going to come from this particular MOSFET. Okay. It is not coming from the op amp anymore. All right. The op amp is not in charge of pushing current. The op amp is just doing its voltage amplification. It is making sure that if whatever is the differential input voltage, this is a large amplification factor times the differential input voltage. Okay. So, for example, if this goes a little low, then immediately this is going to be, if this goes low, then this will go low, immediately this is going to go high. If this increases and this decreases, immediately current is going to be pushed. Okay. So, this is what the op amp does. The op amp is not in charge of supplying power. This large MOSFET over here, this is the power MOSFET. Okay, you are going to use a power MOSFET over here, and that is in charge of pushing power. Now, sometimes you do not even need a dirty supply, right. The supply does not have to be dirty, you still need a regulator. For example, if the load itself is varying with time, okay, sometimes the load is very large, sometimes the load is very small. Okay, small current, large current. If you draw small current, large current from an ordinary power supply, then the internal resistance of that power supply is going to modulate the voltage that you get. Here what is going to happen? If the supply is less, if the requirement is small, then suppose this voltage goes up a little bit, then immediately if this voltage goes up, right, then immediately this the gate voltage of the power NMOS is going to go down, and immediately the current is going to go down. Okay. If the current over here goes down, what gets pushed into the load goes down, so it stabilizes, it brings the voltage down. If, for example, the load starts drawing too much current, suppose I draw extra current from the load, then the output impedance of the circuit, right, there is some output impedance. So, the voltage over here goes down. If the voltage over here goes down, then that gets amplified, right. This also goes up. If it goes up, extra current is pushed over here and it stabilizes the voltage, it pulls it back up. Fine. So, there are two different actions of the voltage regulator. Action number 1 is called line regulation. If I apply a small signal at the dirty supply, how much of that comes out? hopefully nothing comes out, okay, but a fraction of it is going to come out, and that is called, that fraction is called line regulation, and the other is called load regulation. If I increase or decrease the load current, then ordinarily this voltage is going to get increased or decreased, or increased, right. What is the effect of this feedback? How does it adjust itself? How stable is it? Okay. So, for example, if the load current varies by 1%, how much does this voltage vary? Does it vary 1%? Does it vary 0.01%? Okay. So, this is called load regulation. So, you have got two different actions, one is called the line regulation, the other is called the load regulation. How is line regulation taken into account? Suppose this dirty supply increases a little bit, okay. Suppose the supply voltage increases a little bit, it does not matter, right. This feedback loop still ensures that the voltage over here is just right, such that the voltage over here is V ref times R 2 by R 1 plus 1. Okay. So, that is line regulation. Is that okay? First of all, this has isolation, drain to source is isolated, but it is not just that we have over here. It is not just drain to source, we also have this feedback, and the feedback makes sure that this voltage is absolutely steady. All right. So, this is called a voltage regulator. This is the classic voltage regulator circuit that I have in front of you, absolutely classic voltage regulator circuit. This kind of a circuit is used all the time. You can buy these ICs off the shelf. There are 3 terminal ICs, right, with a heat sink. They look like this. I do not know if you have seen them, right. Okay. There is a heat sink, there is a metallic heat sink on the back side. Why do you need a heat sink? All the load current is coming through this power MOSFET, right. Dirty supply minus clean supply times that load current is the heat in this power MOSFET, is the power dissipated by the power MOSFET is dirty supply minus clean supply times the current. So, in the worst case scenario, whatever your load current times dirty supply minus clean supply, that is the power given out as heat in this power MOSFET. All right. Now, let us understand a few things. Suppose I want a clean power supply of 1.2 volt. Suppose I want this to be 1.2 volt. What is the minimum value of the dirty supply that I need? What is the lowest value of the dirty supply if the clean supply required is 1.2 volt? How will you figure this out? First of all, if there is any amplitude on the dirty supply, right, that is going to affect how large this has to be. Okay. But then there is one more thing involved. There is the Vt of this MOSFET. If this is 1.2 volt, however large this power MOSFET is, however small this drawn current is, the voltage at the gate is at least a VT above 1.2 volt. At least, okay, at the very least. I am taking the most optimistic situation over here. Most optimistic situation is when the power MOSFET is really large, such that the amount of current drawn out through the power MOSFET requires absolutely no VGS minus VT, which means that VGS of this power MOSFET is equal to VT, most optimistic, which means that the voltage at the output of the op amp has to be 1.2 plus a VT. Now, if the output voltage of the op amp is 1.2 plus a VT, what should be the value of the dirty supply? It has to be more, right? It can't be less than 1.2 plus VT, it has to be more than 1.2 plus VT, maybe VGST more or some quantity more. There has to be some headroom, and this dirty supply has to be above that. Okay. So, this supply, dirty supply, certainly has to be more than 1.2 plus VT, and that is also a super optimistic situation, because if you want this op amp to be having any gain, right, then the output voltage of the op amp can't be equal to the supply. The output has to be lower than the supply. At the point where the output is equal to the supply, at that point the op amp does not have any gain whatsoever. The gain has become 0, right. The characteristics of the op amp has become flat. So, the op amp characteristics, remember, we have discussed, it looks like this. You want to be in the high gain region of the op amp, not in this flat region of the op amp where there is no gain. Okay. So, if your output of the op amp is 1.2 plus VT, your dirty supply certainly has to be somewhat more than 1.2 plus VT, it is not 1.2 plus VT, it can't be equal. Okay. So, for example, if you leave VGS minus VT of 0.2 volts over here and VGS minus VT of 0.2 volts over here, then this is probably not 1.2 plus VT, it is 1.6 plus VT. Okay. I am just now trying to see how optimistic I was. I really was very optimistic. All right. Now, let us say you have got an amplitude over here of plus minus 0.1 volt. All right. So, the lowest, at the lowest point, this has to be 1.6 plus VT, which means on an average this dirty supply has to be 1.7 plus VT, right. I am leaving headroom of 0.1 volt for that amplitude. I am just assuming 0.1 volt of amplitude is there on that dirty supply. So, now the dirty supply is 1.7 plus VT, the actual supply going to the load is just 1.2 volt. What is the drop over here? It is 0.5 plus VT is the drop across drain and source. Okay. And suppose VT is another half a volt, then that means that the drain to source drop is something of the order of 1 volt. So, I have got a 1 volt drop over here. All right, which means that if my load current, maximum load current is 50 milliamperes, then the heat, the maximum heat in the MOSFET is going to be 50 milliwatts. Okay, which means that the form factor of this particular device has to be such that it can dissipate 50 milliwatts as heat without increasing the temperature of the circuit. Okay. When you increase temperature of the circuit, other funny things start happening, right. VT starts in changing, all kinds of things happening, right. We do not want to go there. we do not want to go into that domain. We want to have some steady state temperature of the circuit, right. We do not want to burn, right. So, our circuit has to be able to dissipate 1 volt times the maximum load current, if that is 50 milliamperes, 1 volt times 50 milliamperes, 50 milliwatts, the load has to be able, this MOSFET has to be able to dissipate that heat safely. So, that is why you need a heat sink. Okay. You need a heat sink, it is a big metallic flat plate behind the device, such that it can throw it out as heat uniformly and nicely without increasing the temperature of the device. All right. So far so good. So, I was drawing 50 milliamperes, 1.2 volt. What is the power delivered to the load? 50 milliamperes times 1.2 volt is the power delivered to the load. 60 milliwatts is the power delivered to the load. What is the power used up over here? 50 milliwatts. 60 delivered, 50 used, net is 110. Okay. What is the efficiency? Efficiency is power delivered to the load divided by actual power drawn from the supply. So, that is 60 divided by 110, okay, it is less than 60%, right, and this is happening in the power supply. Okay, this is a disaster, right. This is outright theft, right. I make a battery, I give you a battery, right, and even before you do anything with the power from the battery, you throw out more than half of it as heat, right, or close to half of it. You just say, sorry, I want a clean power supply, I have to burn half of your battery energy as heat, right. This is outright theft, right. This is a disaster. Okay. So, unfortunately, this is the classical, this is the absolute classic voltage regulator circuit. All right. This is the textbook approach. There is one more approach that we can do. So, a lot of people do not like this, because of course, if the numbers are in favor, suppose I make this larger, okay, the numbers will come in favor if the voltage power supply voltage becomes larger. Suppose instead of 1.2 volt you need to deliver 10 volts, okay, 10 volts over here, right, and add another 1 volt, 11 volt. So, out of an 11 volt supply you are delivering 10 volts, right. Then suddenly your efficiency becomes 10 by 11, which is much better than 60 by 110. Okay. So, it all depends on how large this value is. If this value is large, then you are at an advantage. If this value is low, then unfortunately your efficiency is going to drop like a stone. Now, in modern technologies, the maximum supplies become low. Why? Why? We have not discussed this at all, right. The MOSFET becomes smaller and smaller, right. You want to pack in more MOSFETs in the same area, you want more functionality on one chip, right. You want your cell phone to be a camera and Bluetooth and this and that and GPS and audio recorder and so and so and so and so, right, and you want to play games on it and you want to watch movies on it, right, all in the same handset, right. That basically means that you have to pack in more circuits into the same area, silicon area, which means that you need to make the MOSFETs smaller and smaller in size, right. When you make the MOSFET smaller and smaller, you need to also be able to control the channel in the MOSFET. Okay, to be able to control the channel in the MOSFET when the size of the MOSFET is very small, right, the width of the MOSFET is very small, the length of the MOSFET is very small, everything is small, right. You want to control the charge in the channel, you have to make the thickness of the gate very small, and this is where the disaster happens, right. The MOSFET is like a capacitor, right. You are making the thickness of this dielectric thinner and thinner and thinner, right. In the most modern technologies, 28 nanometer, 22 nanometer, Intel is now at 16 nanometers, right. In these technologies, this dielectric, this gate dielectric is as thin as a few atoms, okay. It is really thin. Now, if you apply a large voltage over here, the dielectric is going to break down, and by breakdown what it means is that it is going to ionize, right. There is going to be some welding action. Have you done welding? You might have done welding in your workshop, right. You bring the rod very close, right, and then the air in between the rod and the surface ionizes. Actually, you have to touch it and then bring it up a little bit. A lot of times your rod is going to get stuck over there. So, when you touch it, you build up the short circuit current, then pull it out a little bit, you get to ionize the air in between, right, and then there is a arc that develops in between, right, through the ionized air. So, the same thing is going to happen over here. You will manage to ionize, and then it is going to break down, and then it is going to fuse. These two are going to get joined. Okay. So, when such a thing happens, the MOSFET is no longer usable. This is, I am drawing it as a capacitor, it is a MOSFET, right, it is some MOSFET is there. All right. So, the MOSFETs in finer and finer technologies can tolerate lower and lower and lower voltages. So, for example, in the latest and I mean in your smartest of smartphones, right, the maximum voltage that the MOSFETs will tolerate is probably 0.6 volts. Okay. What will you do? You still have to regulate the voltage. So, it is not even 1.2 that we want 0.6. You still have to regulate the voltage, the supply is still very dirty, right. You still have to do all of this, and therefore, the efficiency is going to be even poorer than what we are talking about, right. You were unhappy, you were complaining of theft when I gave you 50% efficiency, you drop it to 0.6, it is going to be even further down, 25%, right. So, we have a problem. Okay. The classical voltage regulator used to work in the classical period, right. In the last decade it used to work fine, right, when voltages were higher, when MOSFETs used to be bigger, when people would not demand a camera inside a cell phone, right. In those days this classic voltage regulator would work just fine. In today's day and age, this kind of a voltage regulator is going to give you very poor efficiency. What do we do? So, the answer actually lies in this MOSFET, right. We need to have a power MOSFET over there, but do we have to have it like this? Why not flip it around? Okay. This is your dirty supply. Unfortunately, when you flip it around, this MOSFET starts working like a common source amplifier, right. From if the input is at this terminal, output is at this terminal, then it looks like a common source amplifier. If you think of the input over here, then it looks like a common gate amplifier. Okay. If the input is at the source, dirty supply has a small signal, there it looks like a common gate amplifier, but the output of the op amp is at the gate, there it looks like a common source amplifier. So, we are going to do exactly the same thing. Okay. Now, if there is negative feedback, then the op amp will make sure that these two terminals are equal in voltage, right. So, the current is Vref by R1 over here, that current is drawn through R2 and the output voltage is therefore the same as before, Vref into 1 plus R2 by R1, right. But this is of course, if there is negative feedback. So, all that we now have to make sure is that there is negative feedback. How do we do that? If I do the same signs as before, that is plus on top, minus on the bottom, then unfortunately this is an extra inverting amplifier, right, common source amplifier. This is going to invert once again, you are going to end up with positive feedback. Okay. So, instead what we are going to do is, we are going to place minus over here and plus over here. Okay. So, you flip the signs and that should be enough. For example, if this voltage is too high, suppose this voltage is too high, right, then this is going to be a fraction of that, this is higher than usual. If this is higher than usual, then the amplifier is going to amplify it and make it a lot higher. If this is a lot higher, then the PMOS current is going to go down, right. So, the current output of the PMOS is going to decrease, which means that this voltage is going to drop. Okay. That current is getting pushed into the load. On the other hand, if the voltage over here is low, if this is lower than required, then what is going to happen? The amplifier is going to amplify and it is going to make it a lot lower. If it is a lot lower, then the PMOS current is going to increase in value, it increases in value and then comes into the load and the voltage increases. Okay. So, there is still negative feedback, all I have done is flipped the signs of the op amp. All right. Now, let us do our maths once again, our numbers. Let us run through the numbers yet again. What do we have? We wanted, let us say, an output voltage of 1.2 volts. Okay, that is the output voltage that we wanted. What about this gate voltage? Is it important? Is the value of the gate voltage related to the drain? No. Okay. For example, the drain of this PMOS can be higher than the gate voltage, it does not matter, as long as drain to source to drain is more than source to gate minus V t. Okay. So, typical source to gate minus V t VGST is typically 0.2 volts. So, therefore, this source voltage has to be more than 0.2 volts above 1.2, and then you leave some headroom for this dirty supply, right, another 0.1 volt. So, this means that this should probably be above at around 1.5, okay, lot lower than earlier. In the earlier case, I had it at 1.7 plus a VT. VT I took was 0.5, so I got this as 2.2. Okay. So, in the earlier case, this voltage was 1 volt. In this case, this is just 0.2. All right. So, let us do the same thing. I draw 50 milliamperes over here, right. Power delivered to the load is 50 milliamperes times 1.2. So, that is 60 milliwatt. Power drawn from the source is 50 milliamperes times 1.5, right. Overall efficiency is 1.2 by 1.5, that gets you 80%. A lot better than what we had. 80% means you are now closing in on very high efficiency. Okay. So, this kind of a voltage regulator, this is not the classical one. So, this is called a low dropout voltage regulator. And a lot of people refer to this as an LDO. Okay. LDO stands for low dropout. Okay. Low dropout is this voltage is the dropout. Okay. So, this headroom that you require, this is the dropout voltage. So, in this case the dropout is low. So, this is called a low dropout voltage regulator, and this is going to perform much more efficiently than the classical voltage regulator, right. The classical voltage regulator is the standard feedback amplifier. This one has an extra inverting amplifier. Okay. Instead of buffer, common drain buffer, you have made a common source amplifier over here. That led to, of course, a flipping in terms of sign, but otherwise everything is the same. Fine. Any questions so far? Okay, great. Can you comment, can you think about the difference in the design of, suppose you are asked to design this amplifier and you are asked to design this amplifier. Could you comment on any worries or any good things? Well, one thing that you can directly observe over here is that if this is a 2-pole system, right, if this op amp is going to be 2 stages, it is going to be 2 poles, but this is just a buffer and hopefully it is not going to create yet another low frequency pole. However, over here if this is a 2-pole system, the net structure is actually 3 poles, right. It is as if you have got a 3-pole amplifier and then you are placing it in feedback. All right. Now, when you do that, you have to compensate the 3-pole amplifier and not the 2-pole. I mean, if you just compensate this 2-pole or original amplifier, it is not going to be good enough. You have to compensate this entire 3-pole system. Okay. So, this is going to be much harder, much harder. When you do your compensation of this particular structure, it is going to be much harder because there are 2 poles in this plus one more pole, 3 poles, right. You can pull this third stage inside the op amp, and you can call that as one gigantic op amp, right, which has 3 stages, 3 common source amplifiers back to back instead of 2, right. Now, you have to compensate for that 3 stage amplifier. You remember compensating for the 2 stage amplifier itself required so much hard work. Now, if I throw a 3 stage amplifier at you, it is going to be very, very tough. Okay. So, that is one big problem with this circuit. A lot of people avoid that just by making this a 1 stage amplifier, right. They say let us not bother with a 2 stage amplifier, let us make a 1 stage amplifier over there and sort it out, and then they compensate this overall. Okay. So, we will discuss these things and more in the next class when we further talk about voltage regulators and start looking at the frequency response. Okay. So, thank you.